This video is going to run through several different types of graphing transformations. And in this video, I'm going to be working with a handful of our toolkit or parent functions. The functions that I'll be using in this video are our basic quadratic function. So y equals x squared is a parabola, goes through the origin, the point 1, 1, and negative 1, 1. We'll also be working with x cubed. That one goes up to the right, down to the left, goes through the origin, 1, 1, and negative 1, negative 1. Our square root function, that's kind of half of a sideways parabola, so goes through the points 0, 0, 1, 1, and 4, 2. Square root of 4 is 2. That's how I got those numbers. And then finally, our absolute value function looks like a V, also goes through the origin, 1, 1, negative 1, 1. So there are some other kind of basic parent functions or toolkit functions, but these are the four that I'll be working with in this video. So we're just going to run through all the different ways we can transform a graph or modify an equation and see how that impacts our graph. So we're going to start with vertical shifts. Vertical shifts happen anytime you add or subtract a constant to a function. One thing I'd like to point out here is that when you add or subtract a number to a function, we're doing something that is outside of the function. So this is going to be an output transformation. It's going to impact our y values. I point this out because this is a pattern that's going to hold in this section. Okay, so an example would be the function f of x equals x squared plus 3. My parent function is the x squared. I'm modifying the outputs by doing something outside of that function. And what I'm going to do to my outputs or my y values is just add 3 to them. So to graph this, I'm going to start by just graphing my parent function, y equals x squared. That's my basic parabola. I made sure to include 3 points on that graph, 0, 0, 1, 1, negative 1, 1. So that's y equals x squared. What this plus 3 does to the graph is it's going to add 3 to all the y values, which is actually going to take the graph and shift it up 3 units. So I'm going to take these 3 points on my parent function and just add 3 to their y coordinate or move them up 3 units. So the point at the origin becomes 0, 3, 1, 1 becomes 1, 4, negative 1, 1 becomes a negative 1, 4. I connect the dots and I can see that what's happened is my entire parabola has just shifted up 3. And this will be true regardless of what we start with as our parent function. If we add a constant to a function, that's going to shift it up vertically. It's adding to those y values. All right, here's another example. Let's graph g of x equals absolute value of x minus 2. This is a similar transformation. We have a different parent function. We're going to be working with absolute value of x. That's the graph that looks like a V. And this time our transformation is this minus 2 right here. That's an output transformation. It's happening outside of our function. So we're going to do exactly what it says. It says minus 2. So we'll subtract 2 from all the y values. That's going to take the graph and shift it down 2 units. So I'm going to take my 3 kind of points I had on the graph. The one at the origin goes down 2. It's at 0, negative 2. The point 1, 1 goes down 2. So it's at 1, negative 1. And the same is true with that third point. It's going to go down 2 units. And so what happens is my entire graph has the same shape. It's just been shifted down 2 units. Okay, so with our vertical shift, if we add a positive number, it brings the graph up. If we add a negative number or subtract a value, it's going to bring the graph down. All right, we can also have horizontal shifts. We can shift a graph horizontally, and that's going to look like f of x plus k. So if our addition or subtraction of a constant is happening inside the function, either inside parentheses or inside the square root or inside an absolute value, it's going to be an input transformation, which means it's going to impact our x values. And there's a pattern that's going to occur with input transformations. It turns out with input transformations, we always end up doing the opposite. And in this video, I'm not going to take the time to explain why, but you can do these problems by making tables of values and verify that indeed, when you have input transformations, visually the opposite of what you might think would happen happens. All right, that's a lot of words. What do I mean by that? Let's look at an example. Let's graph f of x equals x plus 1 squared. So my parent function is still the squared. We've got something squared. My parent function is still going to be that basic quadratic function. But notice now the plus 1 is happening inside the parentheses. This is an input transformation. Because it's happening inside the parentheses, it's impacting x values. And we're going to do the opposite. So we're actually going to be subtracting 1 from all the x values. Visually, this is going to take our graph and shift it left 1 unit. With input transformations, to kind of think about what to do, I usually think about how would you solve for x? You would minus 1, so we're going to minus 1 from all the x values. All right, so let's make our graph. Our parent function is y equals x squared, which is that basic parabola. I'm going to take all of my x values, and I'm going to subtract 1, or move them left 1. So the point at the origin, 0, 0 becomes negative 1, 0. And then my point 1, 1 goes left 1, negative 1, 1 goes left 1. And what's happened is my entire graph, my entire parabola, has been shifted left 1 unit. Here's another one. Let's graph f of x equals square root of x minus 2. This is another input transformation. It's going to impact the x values because this minus 2 is occurring inside that square root. With input transformations, we're going to do the opposite. It says minus 2, so we're going to add 2 to all our x values. Visually, this is going to take my graph and shift it to the right 2 units. All right, so this time we're working with a square root. And so my parent function is that square root function. I have that shown on the screen. Goes through the point 0, 0, 1, 1, 4, 2. So what this transformation is going to do, we're going to add 2 to all the x values. And that's going to take the graph and shift it to the right 2 units. So my point 0, 0 becomes 2, 0. 1, 1 becomes 3, 1. 4, 2 becomes 6, 2. And that graph has been shifted to the right 2 units. Okay, so vertical shifts are output transformations. They impact the y values. Your plus a constant is occurring outside of the function. Horizontal shifts are input transformations. They're impacting x values. That plus a constant is going to occur inside the function, and you're going to do the opposite of what it says. All right, so that is shifting graphs. We can also have non-rigid transformations like stretches and compressions. And that occurs when your function is being multiplied by a number rather than added. So here's our general form. If we have y equals a constant times our function, this would be an output transformation if the constant is outside of the function. So it's going to impact the y values. And with output transformations, we do exactly what it says. If it says times k, we are going to take our y values and multiply them by k. So depending on what that number is, we're going to get either a vertical stretch or a vertical compression. And so let's do some examples to see what that visually looks like. Let's graph y equals 2 times the absolute value of x. So we have a 2 outside of our function. That means we are going to take all our outputs or our y values and multiply them by 2. If we multiply our y values by 2, it makes our y values bigger, and it means it's going to stretch the graph out vertically. All right, so in this case, my parent function is that absolute value graph that looks like a V. And then what I'm going to do is I'm going to take each of those 3 points on my graph, and I'm going to multiply the y values by 2. So the point at the origin stays there because we had the point 0, 0. If we take that y value of 0 and we multiply it by 2, it's still at 0, 0. However, the point 1, 1, if I take that y value and I double it, that becomes the point 1, 2. Something similar happens with the point negative 1, 1. I take my y value, multiply it by 2, it moves up to negative 1, 2. And then if I connect to the dots, there's my graph. I have the same basic shape. It still looks like a V, but it has been vertically stretched by a factor of 2. It looks a little bit skinnier because it's been stretched out. All right, what if we want to graph y equals 1/2 x squared? This is another output transformation because the 1/2 is outside of our function. So we're going to do exactly what it says to our y values. So in this case, we'll be multiplying our y values by 1/2. If you're multiplying your y values by a number that is smaller than 1, you're making those y values smaller, and that's going to give you a vertical compression. All right, so let's see what that looks like. My parent function is that parabola, so I've graphed that here with my basic points. And I'm going to take each of these points on the graph and I'm going to take the y values and multiply them by 1/2. So the point at the origin stays there because 0 times 1/2 is 0. The point 1, 1, I take the y value, I multiply it by 1/2, it becomes 1/2. And something similar happens with negative 1, 1. We take the y value, cut it in half, it moves to negative 1/2. I connect the dots, and there's the graph of y equals 1/2 x squared. So this time our parabola has a vertical compression, so it's taken the graph and it's actually squashed it, or the parabola looks a little bit wider in this case. So with vertical stretches or compressions, if that constant k is bigger than 1, that's going to stretch the graph out. If that constant is smaller than 1, that's going to give you a vertical compression. What if our constant multiplier occurs inside the function, inside the parentheses, inside our square root? This is now going to be an input transformation. It's going to impact our x values. And once again, we are going to do the opposite of what it says. If we have k times x, we're going to take all our x values and divide them by k. Again, with input transformations, I kind of like to think about how would I solve for x? I would divide by k, and so that's exactly what I'm going to do to my graph. So let's graph g of x equals parentheses 2x cubed. The 2 is inside the parentheses, so this is an input transformation. I'm going to take all of my x values and I'm going to have to divide them by 2. If I take my x values and I divide them by 2, what that's going to do to the graph is horizontally compress it, squash it horizontally. And we'll see in this case, our horizontal compression actually is going to look a lot like a vertical stretch. So this time my parent function is that y equals x cubed. So it goes through 0, 0, 1, 1, negative 1, negative 1. I'm going to take each of those x values and divide them by 2. So 0, 0 stays where it is. 1, 1, I take the x value, I cut it in half, and I'm at 1/2, 1. Same idea with negative 1, take the x value, cut it in half, it moves to negative 1/2, negative 1. Connect the dots, and there's my graph. I've taken this cubic function and squashed it horizontally. I have a horizontal compression. All right, let's do one more. Let's graph g of x equals absolute value of 1/3 x. We have another input transformation because the 1/3 is inside the absolute value. So we are going to be doing the opposite of what it says, and it's going to be impacting our x values. So technically we need to take all of our x values and divide them by 1/3. But dividing by 1/3 is the same as multiplying by 3. If I wanted to solve for x and I had a 1/3 x, I can multiply everything by 3. What this is going to do is stretch my graph out horizontally. So I'm going to start by sketching that absolute value function, that parent function. It looks like a V. And then I'm going to take each of the x values and multiply them by 3. So the point at the origin stays where it is, but the point 1, 1, when we take that x value and multiply it by 3, it moves to the point 3, 1. The point -1, 1, multiply the x value by 3, it moves to -3, 1. And so graph the function. We have our absolute value v. It's been horizontally stretched, which in this case actually looks exactly like a vertical compression. All right, so with our horizontal stretches or compressions, it's backwards. So if your constant is bigger than 1, you'll be horizontally compressing. If your constant is smaller than 1, like a fraction, you're going to get a horizontal stretch. All right, I've got 2 more different types of transformations to show you, and then we'll put this all together. If we put a negative sign in front of our function, that is going to give us a vertical reflection. So that negative sign in front of the function is an output transformation. It impacts your y values. And so what it's going to do is actually change the sign of all your y values. And that's going to take your graph and flip it over the x-axis. So all your y values change sign. If we have a negative inside the function, that's an input transformation. It's going to impact your x values, which means it's going to change the sign of all your x values. And now you've got a reflection about the y-axis. All right, so let's look at some examples and see what this looks like. Let's graph y equals -square root of x, and then compare that with y equals the square root of -x. So we have the same parent function. For both of these, our parent function is square root of x. The one on the left, the negative, is outside of the function, and the one on the right, the negative, is inside the function. All right, so for both of these, we've got the same parent function, so I'm just going to sketch that right now for both. My square root function goes through the origin, 1, 1, and 4, 2. For the graph on the left, the negative is outside of the function, so that's going to be an output transformation. And I'm going to take all of my y values and multiply them by -1. So the point at the origin stays there. 1, 1 becomes 1, -1. 4, 2 becomes 4, -2. All of my y values became negative. And so what that's done is it's taken my graph and it's flipped it or reflected it over my x-axis. Whereas the graph on the right, square root of -x, the negative is now inside the square root. So what that's going to do is change the sign of all the x values. Origin stays where it is. 1, 1 becomes -1, 1. 4, 2 becomes -4, 2. And so now, when we change the sign of our x values, our graph has flipped or reflected over the y-axis. All right, so we've got 6 basic transformations: vertical shifts, horizontal shifts, vertical compressions, horizontal compressions, and we can reflect over the x-axis or the y-axis. We can also do multiple transformations at the same time. So we can have functions that have several of these different transformations. The order you work with your transformations does actually matter. With output for transformations, we follow the rules of arithmetic. We do what it says. And so we're going to use our order of operations, which means we have to do any multiplication before we can add or subtract. So with output transformations, we have to do our stretching and reflecting first, and then we do our shifts. This just comes from PEMDAS. We multiply before we add or subtract. Input transformations are always backwards. We do the opposite. It's like we're solving an equation. So we're going to have to do our adding and subtracting first, then we'll do our multiplying or dividing. In terms of our transformations, we're going to do our shifts first, then we'll do the stretching and the reflecting. All right, so let's do an example that has lots of different transformations, just to show how this works. So here's my example. It says, use the graph given to sketch the graph of y equals 2, p of negative t plus 2 minus 3. So we have a graph of p of t, so using t instead of x, but same process. And we have lots of different transformations going on here. All right, I'm going to draw my axis first, just so I'm ready to go. So we've got both output transformations and input transformations, things happening outside of the function and things happening inside the parentheses. It does not matter if you do your output transformations first or your input transformations. Totally up to you. I'm going to start with my output transformations. And so there's two things happening outside of this function. There's that 2 times and then the minus 3. So what that means is I'm going to have to multiply all of my y values by 2. That's the 2 times. And then the minus 3, I'm going to subtract 3 from my y values. So I'm going to end up having a vertical stretch by a factor of 2, and then I'm going to shift it down 3 units. I have to do the multiplying before I can do the subtracting. All right, so I'm going to start with the multiplying. To help me, I labeled some key points on the graph that they gave me. So I've got the point 0, 1. When I take the y value and I multiply it by 2, it becomes 0, 2. The point 3, 3, multiply the y value by 2, it becomes 3, 6. 6, 2, double the y value, becomes 6, 4. 7, 0, double the y value, it stays where it is, 7, 0. And then I'm going to connect the dots, giving a similar shape. So notice that the first part of this graph is a curve. So I tried to do that. And then we've got line segments. So over to the right, I have done the vertical stretch by a factor of 2. So our next step is to shift the graph down 3 or subtract 3 from all the y values. So this point 0, 2 goes down 3. It's now at 0, negative 1. The point 3, 6, we bring it down 3. It's at 3, 3. The point 6, 4, down 3. It's at 6, 1. And that last point, 7, 0, goes down 3. It's at 7, negative 3. So I took this graph that's in red, shifted everything down 3 units. So those are our 2 output transformations. We've got our vertical stretch by a factor of 2, and then we shifted that down 3 units. Now we also have 2 input transformations. The input transformations, we would have to do the shift first. So we're going to minus 2 from the x values. That's going to shift it to the left 2. Then we'll deal with the negative 1, which is multiply the x values by negative 1. That's going to give us a reflection over the y-axis. All right, so let's see what that looks like. So again, I'm going to do my subtract 2 first, then deal with the negative. All right, so I erased the thing in red just to keep this hopefully a little bit neater. So I'm going to take all of my x values and minus 2. That's going to shift the graph to the left 2. So this point that was at 0, negative 1, left 2, we're at negative 2, 1. The point that was at 3, 3, I move it left 2, I'm at 1, 3. There was a point at, let's see, 6, 1. I move it left 2, it's at 4, 1. the point at 7, -3, move it left 2, it's at 5, -3. And so that entire graph has been shifted left 2 units. All right, finally, one more transformation to do. That's my reflection. It's going to impact my x values, so it's going to flip it over the y-axis. But basically what I'm going to do is I'm going to take all my x values on this blue graph, I'm going to change their sign, and that's how I'm going to do my reflection. But I'm going to erase this green just so it's easier to see. And now, again, I'm taking all my x values, changing their sign. So this point, -2, 1, becomes +2. I think I said that wrong. -2, -1 becomes +2, -1. And the point 1, 3 becomes -1, 3. And I'm going to connect the dots as I go just because I want to make sure I keep the right shape and not get confused about what gets connected to what. So this is this curved part. We reflected it over the y-axis. This point, 4, 1, is going to become -4, 1. That's connected with a line segment. And then finally, the point 5, -3 gets reflected over and becomes -5, -3. And so in purple, that is my final answer. I've done a total of 4 different transformations on that graph. Let me just erase the blue so it's a little bit easier to see what happened here. So to summarize, doesn't matter if you do your inputs or your outputs first. When you're doing your output transformations, save the shifts for the end. Input transformations, it's backwards. You have to do all those shifts first. All right, that was my last example in this video. Please reach out if anything is unclear.